using any of the path sensitization algorithms. So for path sensitization, what you have to note is that we'll first try to traverse the circuit in one path, right? Like we'll allow the error to feed up to the end. Then we'll try to bring the error backwards, right? And see if it makes sense according to our assumptions. Okay. Now, for the sake of readability, okay, I'm going to represent the input by letters instead of numbers. So let's call this one A, okay, and let's call this one capital B. Let's call this one capital C, and let's call this one capital D. Okay. Now, let's do for A stuck at 0 first. Okay. So when they say A stuck at 0, it means that permanently this one is at 0. Okay, and it's a fault in a circuit. You see, it's not supposed to be so. Okay. Now we are assuming that one, we don't know, like our circuit has a fault. That's our perspective. Our circuit has a fault, but we don't know where the fault is from. So one assumption is that A can be stuck at 0, right? So if A is stuck at 0, then how can we input elements here such that it will test for that particular fault? That's the whole point of test vector and path sensitization. Okay. So if A is stuck at 0, I mean the fault to be somewhere here. Okay, so here we'll have some fault. Now, the first thing you have to note is that if they say A is stuck at 0, like if this fault is stuck at 0, then it means that we have to make sure that we input a value that can prove that it's really stuck at 0. So, for example, if you have a black box, right, and let's say the black box is supposed to output the opposite of what you input it. Okay, it's supposed to output the opposite of what you input it, and you come and input a 1, right, and you get a 0. Okay, now if you input a 0 and you still get a 0, right, you realize that the the correct thing should have been here, should have given you 1, right, but the mistake is that it's giving you a 0. But you see, if you had only tested by inputting 0, if you had only tested by inputting a 1, okay, if you had only tested by inputting a 1, you would have never known that when you input this circuit, when you input a 1, it's like the output is stuck at 0. When you put a 1, it doesn't work. Okay, and so that's our idea. Our idea is to make sure that our input test the fault. So here A is stuck at 0, right? If you input 0, I mean you're already stuck at 0, so we can't check. Okay, so it means that we have to make sure that our input mechanisms work such that here gets a 1 here. Okay, now if here gets a 1, then here's an inverter. Okay, so if the and it's the output of an inverter, so if here is a 1, then it means that the input was a 0, assuming the inverter had no fault. Okay, so it means that B is 0, right? And with that, you've gotten the first test vector B, which is 0. Now we are about to propagate the error forward, okay, because the error is here, so we are about to propagate it forward, right? Now we can either propagate it upwards because we have what the error is connected both to this gate and this gate, so we can propagate it upward or downward. Okay, but for the sake of what should we do? Okay, for the sake of randomness, let's first propagate it downwards. Okay, now if you propagate it downwards, so that we don't get confused, let me call I'll not use a 1 or a 0. I'll just still use the letter A to represent it. Okay, so it means that at this point we have small letter A, right? Now we want to see something like A. We don't want to see 1 or 0 here because we can't differentiate 1 from another one. Like, is the 1 caused by B or is the 1 is caused by C? That's it. Okay, we can't differentiate. So because we can't differentiate, like let's use variables to represent. Okay, so that the difference can work, but you can still use variables if you can differentiate. Now this is an AND gate, right? Right. So you see, if in an AND gate, immediately one of the inputs goes to 0, the output will go to 0, right? A and B, right? If A goes to 0, the output will go to 0. If B also goes to 0, the output will go to 0, independent of each other, right? At the end of the day, we don't know who is causing the 0 to appear, whether it's A or B, right? So it means that since it's an AND gate, we have to what? Fix this input to 1, right? So that you realize that when A is 1, we'll come and wait for B. And if B is 1, we'll come and wait for A. Like it will depend on the other one. We want it to depend on the other one. That's why we are doing this. Okay, so we fix this one at 1, right? And when we fix this one at 1, this is an AND gate, right? So if here is A, then the output will be A, right? Assuming we don't know the value of the fault. Now we come here, right? And this is a not OR gate, right? Not OR, the function is something like this: A or B or bar, right? So that's the not OR function. Now you realize that this function too is an at the very core of it is an OR gate. Okay. Now in an OR gate, you realize that if any of the input is 1, right, then the whole function will go to 1. Like we can't differentiate. So it means that we have to make sure that the one of the input is fixed at 0 so that the output will depend on the other one. So for example, if B is at 0, then we have to come and check for A. If A is at 0, then we have to come and check for B. But if B was at 1, we don't need to check for A before we know that the output will be 1, because 1 or anything will be 1. Okay. So here is the same logic. So because we don't need to check, we don't want to do that check. We want it to depend on this A. That means I will set this one to 0, right? At the end of the day, this is a not also here, instead of here being A, here will be A bar. But it doesn't really matter whether we just want the A to propagate. Okay. Now once you get this A propagating, you are now at an AND gate, right? So at an AND gate, you realize that it's the same logic like when we're here, right? We have to set this one to 1 so that the error A will propagate. So it will propagate, something like this. Now, once you do this, this is called the forward path. You have been able to come from your input all the way to the output, right? So that's the forward path. You have to propagate backwards to test whether your assumption was right. Okay, so that one too is simple, right? So for anywhere which was not along the primary path or the path which you used to go forward, like anywhere you assumed, for example, here we assume that it is supposed to be 0. You go and check even if it is possible. Okay, so let's do for the top. Okay, so here we know that B is 0. Okay, and A is a NAND gate, right? But the NAND gate is outputting 0. Okay, so it's a NAND gate, so it's supposed to be A and some another variable. You let me call here key. I mean, you can put small letter A, but don't let them get confused. So A and K or bar. Okay, now you realize that this is a NAND gate, and for a NAND gate to be 0, both of the inputs have to be 1, right? But we are unfortunate. One of the inputs is coming from the erroneous A, right? It's coming from the erroneous A. So we can't be sure, right, whether we can't be sure whether this can truly be 1. Okay, but still we can just set it that okay, fine, let A be 1, right? And let's assume that this one is also 1, right, for this test case, right? So that the test vector is 1, because here has to be 1 and here also has to be 1 for this one to output a 0, right, for this one to work. So realize that this one, some way, somehow, it depends on the test vector. So this part is generally not favorable, right? It can't really test for the faults, but for test cases, let's hold it first. Now let's go to here. Here we assume that this is the output of an XOR gate. It is 1, right? But one of the input is coming from C, and C is already 1 from our previous assumptions, right? C is already 1. Now this is an XOR gate. The XOR function is what? C D bar or C bar D. Um, that's XOR. That's the XOR function. So this one, the function it's implementing is this one, right? Now we already know that the output is 1. right? But we have one of the inputs already to be 1, right? So C is 1, right? Now if C is 1, then here will go to 0. So we can't consider here. So we may have to make sure this expression is 1. So if C is 1, the only working expression for D to be 1 is that D has to be what? 0, right? So it means that D has to what? Be 0. Because this is an AND gate. Unless this one is 1 and this one is 1. But this is an inverted one, like inverted element. So you have to put 0 there to get the 1. Now once we do that, then we have generated our test vector. Although this one is not really favorable because we couldn't really rationalize what was going on here, whether here is truly a 1 or here is truly a 0, because it was coming from a 40 input. Okay. So one of our test vector is 1, 0, 1. Now let me use a different marker. Or should I clean the whole diagram? Okay, let me use a different marker. So this time we are going in the green. So the first one, we took the lower part. The second one, let's take the upper part. So for the upper part, let's call here A. I mean, here was A. So let's call this one A. Okay. Now, this is an AND gate, right? And the AND gate, you realize that for an AND gate to, like, depend, an AND gate is something like this. A, B, or bar, right? For an AND gate to depend on one of its input, then either one of its inputs should be what? A 1. Right? If any of the input goes to 0, the whole function will come to a 1. So we can't use it. Okay. So it means that here we have to set A to 1 because only A and this small a are the inputs here. So we have to set this small a and this capital A to 1 strictly. Right? So we set it to 1. Then it means that this one can propagate forward as what? A bar. Right? Because if this is 1, then I mean this B, which is representing small a, will be what? Will be left with that small a, then a bar. Now when we reach here, this is a XOR gate, just like previously, but this time around, because you are coming from the top, right, it means that the down one here has to be 0. Okay. Then we also come and get an output of A bar because XOR, right? And now we are also at an AND gate, right? Now it means that here has to be 1 by the same logic, so here has to be 1, and our output will be A bar, right? Now you realize that this one too, we have assumed things. For example, here we assume that the output is 0, right? Now here you realize that unlike the first one where we couldn't tell because we needed both inputs to be 1 and one was coming from a 40 input, this one we need the output to be 0, and this is an AND gate. Immediately C goes to a 0. So immediately C goes to a 0, right? We are more than satisfied, like it has worked, right? Unlike here where we needed this one and this one, here immediately C goes to a 0. We are more than satisfied, it has worked, right? So this test vector with 1, 0, 0 is more favorable than the previous one. You understand? Yes, and you come here to, it's the same thing, except that now here C is 0, right? And the output is 1. So if C is 0 and the output is 1, it means that you can't really use this. You have to use this, right? So if C is 0 and it means that D has to be what? Equal to 1. Okay. So you realize that the green one, the test vector be 1, 0, 0, 1. Whereas the red one, the test vector be 1, 0, 1, 0, right? But because we couldn't really justify the first one, then it means that the test vector we use is 1, 0, 0, 1. That is for A stack at 0. Okay, you understand? So let's do for B stack at 0, right? Now, usually in these questions, you have to take them fourth by fourth, right? So if we are assuming that A stack at 0, then the assumption is that there was no fourth at B, right? So if you are doing B stack at 0, here is 1 point of contention. Okay, so here is stack at 0, right? Now it's stuck at 0. We have to make sure that the input coming here is a 1, right? To be able to, the output coming here is a 1, to be able to synthesize this fault. Okay. Now let's propagate the force forward. So we are at an AND gate. Okay. And let's assume that we are using the variable b so that we don't confuse ourselves. So at an AND gate, it means that then the other input has to be a 1 so that we get a b at the output. Okay. So having a 1 at this output, then we can propagate backwards again to get the other fault. But first, let's do for, I think, let's do for the numerator. Okay. So for at the top, right, this is an XOR gate, right? And you have a 1 at the output, right? In an XOR gate, like I already showed, the function is A or B or bar, right? And to get a 1 from an XOR gate, it means that A and B has to be 0, right? So it means that here has to be 0, here also has to be 0, right? To be able to get a 1 in the backward step. Now we are also at the output of a NAND gate, right? And to get a 0 for the output of a NAND gate, it means that both of the input has to be 1. So it means that A has to be 1, B has to be 1. Sorry, A has to be 1, but here has to be 1. Because here's actually the input. The very edge is the input, it's not B. Right? You see this one is directly connected, but this one has a NOT gate before. Okay. So here has to be 1. But if here is 1, then here has to be what? 0. You get it. So that's it. So generally you have been able to do this. It's the same thing for this. Now if here is already 1, right? If this one is already 1, then it means that C has to be equal to what? 0 to be able to output this 0 coming here. Yeah, it's an AND gate. AND gate, sorry. Yes. So if you want to output 0, just set one of the inputs to 0. Yeah. Then now here C is already 0. We are feeding into an XOR gate, but the XOR gate is supposed to output 1. Right. So but C is already 0. So the same function, C bar D or CD bar. Right. Now if C is already 0, right, it means that this one will go. This one is the one which can work. Right. That means that D has to be 1. Right. So D has to be 1. So you realize that the test vector will be 1, 0, 0, 1, just like the test vector for A. So this test vector can test for, I think, two different faults, two different stackout faults. Yes, I mean, maybe there are other ways to triangulate the problem to the very one, but for now, that's it. Okay, yeah.